Hello lovelies and welcome to today's class. In today's interesting lesson, I'm going to show you how to prove that these two equations are dimensionally homogeneous or consistent. Well, before I start, I need to walk you through the principle of homogeneity. Now, what is this principle? Well, the principle of homogeneity states that expressions on both sides of an equation or a physical relation must be the same. Well, what does that mean? It simply means that the left part and the right part must be the same for the principle of homogeneity to hold true. In a situation whereby we go ahead to prove but did not arrive or could not arrive at the same solution for both sides or on both sides, it simply means that it's either the equation or physical relation is not true or our solution was wrong. All right, let me walk you through this and show you how it is done. The first thing you need to know are the dimensions of your variables, right? We have this is x, it represents displacement. The next one represents initial velocity. This one, the small t here means time. The a means acceleration, and the next one is time as well. So you need to know the dimensions of these variables given in the equation. That's the first one. Number two, you also need to understand that constants, for example, this half, which we have in the first equation, is dimensionless. It has no dimension, right? So we're going to actually throw it away in the course of solving this very problem because it has no dimension unless you know where you're going to get it from. But in physics, this does not have any dimension, so we're actually going to throw it away. For example, numbers like if you have a 2, let's say you have a 2, 2 does not have any dimension, right? Even if you have a 3, 4, 5, it doesn't have any dimension. For example, this 2 pi here, this is a 2 pi, it's a dimensionless quantity. We cannot really find a dimension. Therefore, in the course of solving the second problem, we're definitely going to throw it away because we don't know where to get a dimension. And that is how it works. Now, that's the second thing you need to know. And three, you need to be conversant with basic laws of exponents because that's what's going to help you to simplify the expressions without running into trouble. All right, let me walk you through the solution to see how it works. I'm going to start with the first one, which says that x is equal to ut plus half at squared. Let me clean this one right here so that we can start with the first one. Okay, now here we have x. X is measured in meters, right? And x is displacement. Well, you need to know about these three fundamental quantities, which are mass, length, and time. You need to know this whenever you're doing your dimensioning. You know that we have 7 fundamental quantities. The first one is mass, followed by length, followed by time. The next one is electric current, okay, followed by temperature. The next one is amount of substance. And lastly, we have luminous intensity. These are the 7 fundamental quantities. But when it comes to dimensioning, right, for our level, we actually use MLT, which are mass, length, and time, to work with. So we use the 3 of them for our level. Maybe when you get to a higher level, you start working with the other ones. But for our level, we work mostly with mass, length, and time. All right, so this mass here, okay, represents the units for mass is kg, right? For length, it's meters. For time, it's seconds. Okay, so whenever we're doing dimensioning or testing the dimensional homogeneity of equations or a physical relation, we use the dimensions. These are actually dimensions. We use them, right? We use them for the dimensioning. And what this means is that, for example, as x is displacement, which is measured in meters, right? We are going to replace x with L on the left part. Here is what I mean. Remember that x is displacement, right? And displacement is measured in meters, right? Instead of putting meters for displacement, we put the capital letter L because this is the dimension for displacement, while this is a unit, okay? The capital letter L is the dimension for displacement, while m is the unit for displacement. Okay? For example, if they say you should measure the distance or displacement, you would say 200 meters or 300 meters, right? It's the SI unit for displacement. But when it comes to dimensioning, you use the capital letter, which is the ML2E. So for displacement, it's L, okay? Because displacement is length, and you use the capital letter L for displacement. So on the right, sorry, on the left, we have an L. This is equal to, now for U, the U there is velocity. Velocity. Okay. Now, what is velocity? Velocity is simply the rate of change of displacement with respect to time. That's the meaning of velocity. So velocity is the rate of change of displacement with respect to time. Therefore, we can write it this way: x over t, right? So it's the rate of change of displacement with respect to time, or you can also write it as delta x, okay, change in x over t. Now, this x here, remember that x, the dimension for x is length, okay, which is L. So we say L over the dimension for time. We don't say seconds when dimensioning, we use the t. So we use the capital letter T. Okay. Now, we're not going to leave it like this as it is. This is actually the dimension for velocity. But you can actually take the t upwards. You can take it upwards. If we take it upwards, we shall now obtain L t to the power -1. So if it's at the denominator, that was why I talked about knowing basic concepts in exponents or laws of indices. So if it were at the denominator and it has a positive sign or a positive power, for example, this is the power of 1. If you take it up and remove this, this line here, it's going to carry a negative sign, right? It's not going to be a -1. So let's assume you have L over T to the power -1. If it's in this form, if you take it up, it's not going to be L T to the power +1, something like that. So the sign changes when you take it up. This is just a simple way of doing this. Now, this is the dimension for velocity. We're not going to replace this u here with Lt to the power -1 because that is its dimension. That the dimension for velocity is Lt to the power -1. And the next one, remember that the t here multiplies the velocity. We are replacing all this with their respective dimensions, and that's what we're doing right now. The t, the dimension for t, remember that t is measured in seconds, so the dimension for t is the capital letter T. Okay, we've gotten the dimension for time. We have a plus here, half. Now, the next one is the dimension for acceleration. What is acceleration? Well, acceleration is simply the rate of change of velocity with respect to time. Okay, so it's the rate of change of velocity with respect to time. So we can now say acceleration, this is equal to, or we can say V over T. Okay, now the rate of change of velocity with respect to time. How are we going to get the dimension for acceleration from here or from this expression? Remember that our velocity is equal to Lt to the power -1. That is the dimension for velocity. Instead of starting to get the definition for velocity, we simply replace the V we have here with lt to the power negative 1 over. Now, the dimension for t, which is time, is what? T. Here we have a t here. Okay? The dimension for time is t, while the units is seconds. Remember the difference between dimensions and units. Okay? They are kind of related, but when it comes to testing for the dimensional homogeneity, we mostly use this one. Now, remember what I told you initially, that you can transpose this t, it goes from the denominator and it goes upwards. If it goes upwards, remember it has a positive value here, right? At the denominator, it has a positive value. So if we take it upwards, it's now going to be lt to the power negative 1. This is the first t there. Now, this second t now becomes t negative 1. Okay. And remember from the laws of exponents, remember that these two are multiplying. The first t is multiplying the second t. And from the laws of exponents, if you have two bases that are multiplying each other, two like bases that are multiplying each other's, you can add their powers. Okay? So here we have lt negative 1 plus negative 1. All right. Something like this. If the bases are the same, if you have a squared times a cubed, this is equal to a 3 plus 2 or 2 plus 3, whichever way you want. Addition is commutative, so it doesn't matter the order. So if the bases are the same, simply add their powers. And that's also the same concept we're going to apply here. Since the bases are the same for the t and the t, and we have a negative 1 plus a negative 1, so negative 1 plus negative 1 gives you lt to the power negative 2. This now becomes the dimension for acceleration. Okay, remember that we got it from its definition. And from there, we replace the v and the t with its respective dimensions, and we have gotten to this point. You can choose to have it at the back of your head or understand how this is done. So the dimension for acceleration is L2 to the power negative 2. Now we're going to replace L2 to the power negative 2, or we're going to replace this A here with L2 to the power negative 2, which is its respective dimension. I'm going to do it here. Here we have Lt to the power negative 2. And the last one is the time. Remember, it is squared. And the dimension for time is what? T. It's squared. So this is going to be t squared. All right. Now, let's go ahead and simplify this expression before us. I believe you've understood how to get their respective dimensions. The first thing you need to know is to identify the given variables in the equation. And then with that, you will be able to find their dimensions. And also remember that these numbers, for example, half has no dimension. It's dimensionless, so we are not actually going to do anything with it. Now, since we have an L on the left, according to the principle of dimensional, the principle of homogeneity, if you have an L on the left, you must end with an L on the right. That is the principle. If we have an L on the left and end with LT on the right, then we're wrong. Okay? You must end with an L on the left and L on the right for that principle to hold true. Now let's simplify. We have an L here is equal to, here we have L, okay? And if you look at this, we have a negative 1 here. This is a negative 1, and this is a positive 1. Remember from what I showed you here, okay? If the bases are multiplying each other and they are the same, you simply add their powers. Here you have a negative 1, and here you have a 1. Since they are both like bases, we shall now obtain negative 1 plus 1, right? It's not going to be negative 1 plus 1 because the bases are the same. So we simply add their powers. Next up, we have plus half. Okay, here we have Lt to the power negative 2. So if you distribute this 2 across what's in the bracket, we shall now have t to the power 2. Okay, now you also need to know that if there were other terms in this bracket, these two will be distributed across everything in that bracket, provided they are just multiplying and not adding or subtracting. Here we have also an L on the left. This is equal to, okay, now for this one here, we have an L, okay, minus 1 plus 1 gives us a what? Gives us a 0. Here we have t to the power 0 plus half, okay, L minus 2 plus 2. Remember that they are the same bases. T and t are the same and they are multiplying. So here we have minus 2 plus 2. It gives us a 0. Therefore, we have t raised to the power 0. I'm taking it step by step for clarity purposes. And lastly, let's see how we can work this through. We have an L here on the left is equal to L. T raised to the power 0, okay, is equal to 1. When you have, let's say, a raised to the power 0, according to the laws of exponents, this a is equal to 1. So if t is raised to the power 0, it means that this t is now equal to 1. And 1 times L gives you only L plus half L. Okay. Now, this one here is also 1 because any number raised to the power 0 apart from 0 is equal to 1, right? Therefore, t raised to the power 0 is 1. 1 times the L will give us an L. Remember that this half is dimensionless, so we can easily get rid of it. And we shall now have L equals L plus L. Remember that the half is dimensionless. Just get rid of it, throw it away. Now, we have an L on the left. We have L plus L. They are like terms. Since they are like terms, we can now say L equals L plus L gives you a 2L. And also remember that according to what I told you, this 2 here is dimensionless. So you can say, but 2 is dimensionless. Therefore, L equals L. This you can say it is correct. Okay, now let me explain this part again. Remember that I said that the numbers like this, or maybe 3, 4, 5, 6, 7, they are all dimensionless. You cannot determine their dimensions. Therefore, whenever you find them, you just throw them away. They don't make any sense. For here we have on the left L, and on the right we have L plus L, which are like terms, just like when you have x plus x, it will give you 2x. In this case, we have 2L, L plus L, which simplifies to 2L. Because 2 is dimensionless, we cannot find the dimension. Therefore, we throw it away and say it is dimensionless. And finally, L equals L, because we have an L here and an L here. Having thrown the 2 away due to its dimensionless nature, we're now left with L equals L. And that means that this physical relation or equation is dimensionally correct. Hence, the principle of homogeneity holds true for it. Now, let's go ahead and solve the second problem. Now, let's go ahead and prove that this formula, which can also be called an equation, is dimensionally correct or homogeneous based on the principle of homogeneity. This is a formula for finding the time period of a simple pendulum, and it looks quite tricky, but it's not really difficult. Let me show you how to do this. There are 2 ways that I'm going to show you right now, and it's going to be pretty easy. The first thing that you need to do here is to identify your variables and find their respective dimensions. This is the time, which is represented by capital letter T. The L, next one here, which is the L, is the length of the pendulum. The one underneath is g, which is gravity, right? The 2 pi is dimensionless. It does not have any dimension. Therefore, we can say we want to find the dimension. We shall only find the dimensions of t, l, and g. And t is a period which is measured in seconds, right? Remember, we have m, l, t, right? Now, this t here is the dimension for time. Therefore, the t is equal to t. T equals t, which means that the dimension for the period is t, right? Now, the next one is the L. The L is the length of the pendulum, and it is measured in meters. This L is measured in meters, and the dimension for length is L. The dimension for length is L. Remember, this is mass, length, time. Mass, length, time. This is the dimension for mass, which is the m. The next one is the dimension for length, which is capital letter L. And lastly, the capital letter T is the dimension for time. We can now say L is equal to capital letter L. And lastly, the G here is the acceleration due to gravity, right? The acceleration due to gravity, it is measured in meters per second squared. And you know that acceleration is the rate of change of displacement, not displacement, velocity, with respect to time. So it's also going to have the same dimensions with A, okay? So acceleration and G, okay, have the same dimensions because they are both measured in meters per second square. They have the same SI units, and since they have the same SI unit, they're also going to have the same dimensions, right? So this means that, remember from our previous example, that acceleration, okay, is equal to Lt to the power -2, okay? And G also has the same dimension, Lt to the power -2, because they both have the same SI unit. If you look at this SI unit here, meters per second square. What does this mean? So this is the meter. The meter is the SI unit for length. You can see that the L is right there. And then the next one is underneath it, which is the second square, right? Now, if you have something like this, meters over second square, right? If you take this second square upwards based on what we've been doing, it's not going to carry a negative sign up here. Instead of the positive, it's not going to be -2. Remember, I told you that for easier simplification, simply remove the denominator from where it is and take it to the numerator. But the sign is going to change. The power is going to change. If it's a positive down there, it's not going to be negative when you take it up. If it's a negative down here, if you take it up, it's not going to be positive. So that's exactly what we did with this. And that's also what I've done with this to show that they are both the same and they have the same SI units and the same dimension. Now, what we're going to do right now is that we are going to replace the L and the G with the respective dimensions and also the T with its dimension. But first, I'm going to remove this 2 pi here because it is dimensionless. Therefore, we shall now have T equals the square root of L over G. Remember that this 2 pi is a dimensionless quantity. It has no dimension. Therefore, we are not going to work with it. It's kind of not useful at all. Now, at this point, what's the next thing to do? To remove this square root, I'm going to simply square both sides. I'll square both sides. The reason why I'm squaring both sides is because I want to remove this square root right here. And mathematically, it is correct to cancel this. This square inside the bracket can cancel out with the power of 2. And when that happens, you now distribute the 2, okay, across this one here, we shall now obtain t squared, okay. We have a t squared here is equal to, remember this square has cancelled with the power of 2 or with the square outside, and now we have L over G. Now next up, we are going to replace the L and the G with their respective dimensions. This t here is as it's supposed to be, so there is no need of making or doing any other replacement. It's just as it is supposed to be. If we do that, here we have a t squared equals, the dimension for L is simply length, which is L, over the dimension for G, which is acceleration due to gravity, is Lt to the power negative 2, right? That's the dimension for what do we call it? For acceleration due to gravity. We have Lt to the power negative 2. Remember what I told us initially? If we're taking it from the denominator to the numerator, or if we're taking it up from here, if the sign is negative, it's not going to be positive upwards. And if the sign is positive down here, if you take it up, it's going to be negative. Now, let's do that very quickly to help us simplify this expression easily. Here we have a t squared equals, we have an L here. If I take this entire Lt negative 2 upwards, we shall now have L minus 1, right? Because the L has a power of 1 down here, which is positive. So if you take it upwards, it now carries a negative 1 as its power. Now the t has a negative 2 down here. If you take it upwards, it's not going to be a t squared, right? Because it's already negative down. If you take it upwards, or if you remove it from the denominator, it's not going to be positive. Now, what do we do at this point? Let me explain. Remember, I said if the bases are the same, you simply add the powers, right? Now we have an L here, and this is a positive 1. It's raised to the power of a positive 1. Now we have L, because the bases are the same, we simply add the powers. We have 1 plus negative 1. We've added the two of them together. And next up, we have a t raised to the power 2. Let's simplify further. Here we have a t squared equals L raised to the power 1 minus 1 will give us L raised to the power 0, because 1 minus 1 is going to give us a 0. And next up, we have a t squared. Remember that any number raised to the power 0 apart from 0 is equal to 1. Therefore, this is now going to be t squared equals, this one is just a 1, and 1 times t squared will also give us a t squared. Next, to solve finally for t, or to remove this square, we simply square both sides. We square both sides of the physical relation. This square mathematically can cancel out with this. This also cancels out with this. Now, why am I doing this? For example, let's say you have v squared equals 4. Okay? Now, you can't just leave this like this. You have to solve for v. I'm showing you why we're canceling this out, why the squares are canceling out. If they say v squared is equals to 4, you can square both sides. If you square both sides, the square on the left can cancel out with this, and we have that v is equal to the root of 4, and v is equal to square root of 4 will give us a 2. So that's exactly what I'm doing right here. By squaring both sides, we simply cancel the squares. Now, what are we left with? We're left with t equals t. And what does this mean based on the principle of homogeneity? It means that this equation or physical relation is dimensionally homogeneous, or it is correct, right? Because we started from t equals 2 pi multiplied by the square root of L over G, and we've simplified it to this point. We've reached the point where the left-hand side equals the right. Therefore, we can now say that this equation of physical relation is correct. Okay, so this is correct based on the principle of homogeneity.